All right, so what's going on, y'all? So we got 211, same thing as the other ones, right? Determine nodal displacements, forces in each element and their reactions using the direct stiffness method. This one, a little bit easier because we have one less spring, but let's go ahead and get started. All right, so first step, this is the first problem we encounter that it is not in the correct unit, so it's 1,000 newtons per meter. Delta's in millimeters, so we got to convert that delta. Or you could convert these, but delta's easier. So that's going to be 0.02 meters. So just keep an eye out for those conversions. First step, like always, right, this is our main goal. For those that have not watched any other videos, it's force vector is equal to global stiffness matrix times your displacement vector. So step one, I'm gonna go ahead and write that equation. There's 3 nodes, so there's gonna be a 3x3 matrix. There's gonna be 3 forces, and give me a second. All right. So it's nodes 1, 2, and 3. It's nodes 1, 2, and 3. I like to give myself some room just in case. And then the displacement vector. So it's U1, U2, and U3. Right? So first matrix. This one, K1 is equal to 1,000 newtons per meter, and then K2 is equal to 3,000. So check it out. The first spring is between nodes 1 and 2. So that means here on the matrix, it's between 1 and 2, 1 and 2. So it's 1,000, negative 1,000, negative 1,000, and 1,000. Next one, it's 3,000, and it's between nodes 2 and 3. So between nodes 2, 3, 2, 3. So it's going to be 3,000 plus the 1,000 that's already there. That's going to be a 4,000. And then negative 3,000, negative 3,000, and 3,000. So we got the global stiffness matrix. Now we have to do our boundary conditions. So node 1, no matter how much force you put at 2 or 3, it's never going to move. It's fixed. So U1 is equal to 0. Okay, what else? They give us the displacement at node 3. That is 0.02 meters or 20 millimeters. But remember to convert, so it's 0.02. They give us, no, we're looking for the force at 3, and we're looking for the force at 1. We see that there's no force being applied at 2. It's kind of just in the middle between them, right? Kind of just going left and right, depending if you're pushing or pulling. But force of 2 is 0. Nothing's going on at that node. So these are called loads, not really boundary condition, but just doesn't matter. And again, for those that haven't been watching, you know you're doing something right if you know the force or the displacement, one or the other. You never get both. You're usually looking for the other, right? In this case, at node 1, we don't know the force, but we know displacement. At node 2, we know the force, it's 0. We don't know the displacement. And at node 3, we know the displacement, but we don't know force. So 3 equations, 3 unknowns. It's what we're going to have. F1x is equal to 1,000 times 0 minus 1,000 U2 plus 0 times 0.02. So next one, 0 is equal to negative 1,000 times 0 plus 4,000 times U2 minus 3,000 times 0.02. That number is 60. Next one, F3x is equal to 0 times 0 minus 3,000 U2 plus 3,000 times 0.02, which is plus 60. All right, we got 3 equations, 3 unknowns. So, right, and just by looking at it, we could solve for U2. Just move 60 to this side and divide by 4,000. So if you do that, move 60 over here, then 60 divided by 4,000, you're going to get U2 is equal to 0.015, and that's in meters. Again, this was from equation 2. Let me write that here. From equation 2. Step 4. Now that we have U2, we could find F1x, right? Just plug in U2 and F3x. So if you do that, let's do equation 1 and 3. So you'll get F1x is equal to, plug in negative 1,000 times this, that is negative 15 newtons going this way, or it's 15 newtons going this way. And then F3. F3x, plug in 0.015 into here. Do the math, you'll get F3x is equal to 15 newtons going this way. So it makes sense, right? If there's nothing going on at node 2, hold on, let me box this up. If there's nothing going on at node 2, that means the force here has to equal the force 1 in opposite directions. So in this case, you got 15 newtons pulling at force 3. You got 15 newtons pulling at force 1. Equal and opposite. All right, that was pretty easy. We only have 2 springs, so that's why this problem didn't take too long. Now let's do the elements. So it's between nodes 1 and 2. So I'm gonna do F1x, F2x, and it's the first spring, so it's 1,000. So the matrix is gonna be a little 2 by 2, 1,000, negative 1,000, negative 1,000, and 1,000. And then again between nodes 1 and 2, so your displacement vector is U1, U2. U1 is 0, U2 is 0.015. That's what it looks like. So solve for it, you will get element 1. So F1x of element 1 is equal to 1,000 times 0 minus 1,000 times 0.015, which is negative 15 newtons going this way, or is equal to 15 newtons, whatever way you like to denote it, going that way. F2x will be, of element 1, will be negative 1,000 times 0 plus 1,000 times 0.015. That is going to be 15 newtons going that way. So let me go ahead and box it like this. That's the first one. We'll verify these in a second. Next one, between nodes 2 and 3. So it's going to be F2x, F3x. That is equal to the matrix, but it's not 1,000, it is 3,000 this time. So 3,000, negative 3,000, negative 3,000, and 3,000. And then it's again between nodes 2 and 3. So that vector here is U2, U3, which is 0.015. And 0.02. There you go. Let's keep solving, right? F2x of element 2 now is equal to 3,000 times 0.15. That is 45 minus, well, it would have been plus, but negative. So negative 3,000 times 0.02, that is minus 60. So that means that this is negative 15 newtons going this way, or it simply means that it is positive 15 newtons going the other way. So we got that one. Next one, F3x of element 2 is equal to, it's negative 3,000 times that, so it's negative 45 plus 3,000 times that plus 60 is equal to, I'll put it here, F3x of 2 is equal to 15 newtons going that way. So it makes sense, right? Look, let me box them up. Check it out. So the forces here have to equal the sum of the forces here. Let me tell you what I mean by that. So force 2 in this case, there's no force, right? We determined that it's 0. So that means all the F2x's here have to add up to 0. So we got 15 newtons going to the right, 15 newtons going to the left. There's no more F2, so it's only these two. They cancel out, right? Equal and opposite, so boom, that's 0. We're good. F1x, we determined it's 15 newtons to the left. There's no F1s here, only here, and it's 15 newtons to the left. Boom, matches. F3x, 15 newtons to the right. There's no F3s here, only this one, and that is 15 newtons to the right. So that means we did it right. So this one's pretty easy. I'm considering it was one less spring, but there's your answer.